Usually when you sit down at your keyboard to, write some software, there's this really fundamental, almost physical comfort in the determinism of it all.
Oh, absolutely.
You
Yeah.
write a function, you pass it variables, and it just executes the logic you designed.
Mm.
And if it fails, well, there's a stack trace pointing you directly to the broken logic, right?
Right, yeah. Because every single behavior in traditional software is explicitly programmed by a human being at some point in that chain.
Exactly.
Even the most, complex microservice architectures are ultimately just these massive webs of human intent. The machine isn't inventing new behaviors, it's just executing your instructions at scale.
Right. But then, and this is why we're here tonight,
Mm.
you look at what's happening right now at the bleeding edge of artificial intelligence, specifically with large language models.
Yeah.
And that predictability just completely evaporates. It's gone. The machine stops behaving like a straightforward engine and starts behaving more like like a complex biological system.
It really does. It's wild.
So welcome to another deep dive. Tonight, we're keeping the lights low and the focus razor sharp because this session is tailored specifically for you.
Mm.
As a software engineer, you know how systems are supposed to scale, right?
Yep.
You spin up more server instances, you increase the database size, and the application just gets faster. Or it handles more concurrent users. The improvement is strictly proportional.
Linear.
Linear.
Yeah.
But tonight, we are looking at notes from an LLM mastery series that just blows the very concept of linear scaling completely out of the water.
It does, because we're looking at a phenomenon where scaling up the compute, the data set, and, the parameter count of a system, it doesn't just make it linearly better at its current tasks.
Right.
Scaling it up makes it suddenly capable of entirely new behaviors that literally no one explicitly programmed it to do. It develops tools it was never handed.
Okay, let's unpack this.
Yeah.
Because to a classical software developer, that sounds uncomfortably close to science fiction.
Oh, for sure.
The mission for our deep dive tonight is to explore this exact phenomenon, which the researchers in our notes are calling emergent abilities.
Right. Emergent abilities.
We want to figure out the actual mechanics behind these nonlinear leaps in capability that happen simply by, making a neural network bigger. And the source material draws this direct comparison to phase transitions in physics, which I just find to be a brilliant mental model.
It's a great way to think about it, yeah.
Think about heating water. You bring it from 30 degrees to 80 degrees and then to 99 degrees Celsius. The entire time, you're pumping energy into the system, but fundamentally, it remains a liquid.
Yeah, it's just hot water.
Exactly.
Yeah.
It doesn't get slowly more steamy as the temperature rises. The state remains totally constant until the exact moment you hit 100 degrees.
Right.
Boom. The thermal energy overcomes the intermolecular bonds, and the liquid rapidly expands into a gas. The system fundamentally changes state.
So what does this all mean for how we actually build these things? Well, the underlying mechanism there is what makes that physics analogy so potent for software engineers. In physics, the phase transition happens because the microscopic interactions between molecules reach this critical threshold,
Right.
Triggering a sudden shift in the macroscopic property of the material. In neural networks, a parallel shift occurs within the internal representational geometry of the model.
Internal geometry, yeah.
When you add billions of parameters to a language model, you aren't just giving it a bigger hard drive to memorize more text, you're actually expanding the dimensionality of its vector space.
Okay, so instead of a single database schema where you only have a few columns to store basic statistical correlations like the word dog often follows the word good, a massive network has the dimensionality to store highly abstract, multi-step logic paths.
That maps perfectly onto the architecture, yeah, because a small model just has a low-dimensional vector space. It simply lacks the connective tissue to hold on to complex patterns.
That drops them.
Exactly. If you try to force a small model to track multiple variables across a long paragraph, the vectors collapse. It loses the state. But once the network hits a critical mass of parameters, usually crossing into the tens of billions.
Which is huge.
Huge, yeah. That internal geometry becomes sufficiently high-dimensional, and suddenly the model can plot relationships between concepts that were previously just too distant to connect.
Wow.
The capability to reason abstractly emerges not because we wrote some new reasoning algorithm, but because the space itself became large enough to map the logic.
Which means the pure infrastructure dictates the limits of the logic it can run.
Huh.
I mean, as an engineer, that's wild to wrap your head around.
It really is.
No developer sat down and wrote a pull request for a reasoning engine feature. The researchers just poured in more data and more compute, and the system's vector space expanded until it organized itself to unlock that tool.
Yep. Completely self-organized in that sense.
But, theoretical phase transitions in vector spaces only take us so far. We need to look at the hard empirical data to prove this isn't just a localized fluke in, like, one specific OpenAI or Google model.
Right, and the research community recognized that exact skepticism. They knew they needed a really rigorous, systematic way to test for these sudden leaps in capability across the entire industry.
And that's where Big Bench comes in.
Exactly, Big Bench, which stands for the Beyond the Imitation Game benchmark. It's this massive collaborative suite of over 200 highly difficult, varied tasks.
And these aren't just simple fill-in-the-blank tests either. The notes detail tasks ranging from translating obscure Persian poetry to playing a game of chess entirely via text notation.
Which is incredibly hard for a language model.
Right. Or tracking hidden states in a complex logic puzzle.
Hmm.
The creators specifically designed these tasks to practically impossible for the language models that existed at the time the benchmark was published. They were trying to build a brick wall that, statistical parrots just couldn't fly over.
And the results from Big Bench systematically documented the phase transition phenomenon across the board. They evaluated multiple model families' entirely different transformer architectures, developed by competing organizations, trained on totally distinct data sets.
So it wasn't just one company's quirk?
No, the pattern held regardless of the origin. Across dozens of these highly complex tasks, smaller models just flatlined. They hovered near 0% accuracy, essentially guessing randomly or hallucinating broken text.
Yeah.
But the moment those models crossed specific size thresholds, usually right around that 70 to 100 billion parameter mark, performance spiked almost vertically. The emergence was mathematically real and highly replicable.
Okay, here's where it gets really interesting, especially from a user interaction standpoint. The notes highlight two landmark examples of emergence that fundamentally changed how we as developers interface with these models.
Few-shot learning and chain of thought,
Yeah.
right?
Yes, exactly. Let's break down the mechanics of those, starting with few-shot learning. In traditional machine learning pipelines, if you wanted a model to classify user feedback into specific sentiment categories, you had to fine-tune it.
Oh, yeah, a total nightmare.
You'd spend days feeding it thousands of labeled examples to manually update its underlying weights. But few-shot learning bypassed that entirely through a process called in-context learning. You simply provide 3 or 4 examples right there in the text prompt, ask it to categorize a new piece of feedback, and it executes perfectly.
The mechanical shift required to pull that off is staggering, honestly. The model has to temporarily bind the concepts provided in your prompt without permanently altering its underlying neural weights.
Right, on the fly.
Exactly. It utilizes its attention mechanism to allocate tokens in the context window, essentially building a temporary set of rules. If you attempt in-context learning on a small model, it breaks down completely. Yeah, the small model begins hallucinating or enters this repetitive generative loop, just spitting your prompt right back at you. It lacks the attention heads and the representational capacity to hold those examples in its working memory and apply them to a novel input.
It just sees text and tries to autocomplete it.
Yeah.
It doesn't recognize the pattern you're trying to establish at all.
But cross that parameter scale threshold, and the attention mechanism becomes robust enough to map the dependencies. The massive model dynamically adjusts its behavior based purely on the context window. It learns the task in real time. 0 weight updates required.
That's incredible.
Yeah.
And taking that a step further, the notes dive into chain of thought reasoning, which feels even more alien. This is the phenomenon where you prompt the model with the simple phrase, "Let's think step by step."
Yeah.
In practice, it's essentially forcing the model to do rubber duck debugging inside its own context window.
That is a highly accurate way to frame it, actually. Chain of thought is a massive breakthrough for complex problem solving, particularly in math and logic puzzles. If you feed a complicated word problem to a language model and ask for the final answer directly, it will usually fail. It tries to jump straight to the conclusion across a massive conceptual gap.
Just guessing, basically.
Pretty much. But by forcing the model to output its intermediate steps, to write out its internal logic token by token before arriving at the final answer, its accuracy skyrockets.
because it's allocating tokens in the context window for intermediate state tracking.
Hmm.
It's using the generated text as an external scratchpad to hold variables rather than trying to compute the entire logic tree in a single forward pass.
Exactly.
But again, the big bench data shows this only works if the model has a massive parameter count.
Yeah, small models fail spectacularly at chain of thought. If you instruct a 10 billion parameter model to think step by step, it generates a chain of completely flawed, nonsensical logic that just leads to an incorrect answer anyway. Its attention heads cannot maintain the logical thread across multiple sequential steps. It drops the state halfway through the explanation. But once the network scales up to that 100 billion parameter range, scale alone unlocks that hidden gear.
Wow.
The high-dimensional space allows it to map the dependency chain perfectly, holding the intermediate variables in context and arriving at a sound conclusion.
Okay, I need to put on my skeptical engineer hat here,
Please do.
because my natural instinct, and probably the instinct of anyone listening who spends their days hunting down flaky tests in a CI/CD pipeline,
Yeah.
is to look for the flaw in the measurement suite.
Absolutely.
If I'm looking at a Grafana dashboard and I see a performance metric flatlining at absolute zero for months, and then it instantly spikes to 80% in a single deployment, I don't assume the system magically learned a new skill.
No, you assume your logging is broken.
Right. I assume my logging pipeline was broken, or the rejects evaluating the metric was fundamentally flawed.
Yeah.
We have to ask, is it possible we are just mismeasuring this entire phenomenon? Are we using discontinuous evaluation metrics that hide massive amounts of gradual background improvement happening under the hood?
Well, this raises an important question, and it sits at the absolute center of an intense, active scientific debate documented right in our source material. The skepticism you're expressing is the exact argument being published by several prominent AI researchers right now.
Really?
Yeah. The debate hinges entirely on the mechanics of discontinuous metrics versus continuous metrics.
Let's define that for the audience real quick. A discontinuous metric is a strict binary pass-fail test. Think of a strict regex looking for an exact string match. Let's say the task is a complex, multi-step math problem, and the final correct answer is a specific 5-digit number, like 42,561.
Okay.
If you evaluate the model's output using a strict pass-fail metric, the model gets a 0 if it outputs literally anything else.
Right. And consider the internal token probabilities during that test. Imagine a small model outputs total gibberish. The probability it assigned to the correct digits was near 0.
Makes sense.
Now, a medium model outputs a string of 5 numbers, but they are the wrong numbers. However, its internal softmax layer might be assigning a 10% probability to the correct digits, up from 1%.
Ah, okay.
Then a larger model gets the math mostly right, but carries a 1 incorrectly and outputs 42,560. Its internal probability for the correct answer was 80%, but it missed by 1 digit. Under a discontinuous metric, all 3 of those models score a flat 0.
Right, the regex fails them all equally. Then the massive model finally nails the formatting and the exact math, outputting 42,561. It scores 100 points.
Yeah.
So in the big bench graph, it looks like this sudden magical phase transition from 0 to 100% capability.
Exactly. But if you strip away the strict string matching and instead evaluate the continuous metric, the actual log loss function, measuring the probability distribution the model assigned to the correct tokens, you see a very different picture.
A smooth curve.
Yes. The underlying math shows a smooth, predictable, gradual improvement as the model scaled up. The network was getting mathematically closer and closer to the right answer, but the strict, discontinuous testing suite was masking that progress until the model finally crossed the finish line.
So that implies the emergence of these abilities is just an illusion created by poorly designed unit tests. If we just measured the vector distances properly, the magic disappears into a predictable scaling law.
Well, the synthesis of the current research suggests the reality is vastly more nuanced than a simple etherer.
Okay.
It is partially a measurement illusion caused by strict scoring, but the nonlinear leaps are still a very real structural phenomenon.
How so?
When researchers switch their evaluations to continuous metrics, the smooth curves appear for basic knowledge retrieval. However, for highly complex tasks, specifically those requiring multi-step logical structuring like chain-of-thought reasoning, they still observe aggressive, nonlinear jumps in the probability distributions.
Oh, I see. It's the cognitive difference between learning vocabulary and suddenly understanding grammar. You can memorize individual words smoothly and linearly all day long. But the ability to construct a complex, grammatically dependent sentence isn't just the sum of the vocabulary words.
Right,
It's
exactly.
a distinct structural leap in capability.
Yeah.
Which brings us to a highly uncomfortable reality for anyone who builds, tests, or deploys software for a living. We have to confront the AI safety dilemma.
Yeah, this is where the theoretical physics analogies and the debates over vector spaces just crash into the reality of deploying code into production environments.
Really?
The unpredictability inherent in emergent capabilities fundamentally breaks traditional safety alignment.
Think about this from the perspective of writing a robust CI/CD pipeline. You wrote unit tests, integration tests, and end-to-end tests based on the known boundaries of what your software is capable of doing. You test for edge cases within those parameters. But how on earth are you supposed to write a safety test for an emergent ability you literally cannot foresee? If you're building version 2.0 of an LLM, and you know that scaling the parameter count by an order of magnitude might suddenly grant it the ability to, say, write highly evasive polymorphic malware,
Terrifying.
or dynamically manipulate human psychological vulnerabilities, abilities that simply did not exist in version 1.0. How do you test for that in advance? It violates the core tenet of software engineering that system behavior must be bounded and predictable.
And the industry is genuinely struggling to architect a solution to that paradigm shift. Safety alignment is no longer just about preventing known harms or filtering toxic outputs.
Right.
It has morphed into the impossible task of anticipating unknown unknowns. You are scaling up a massive mathematical black box, and you are hoping your alignment techniques are robust enough to contain whatever new cognitive tools jump out of the box once the training run finishes.
And if we look at the historical data in the source notes, we can actually see this exact unpredictability burning developers in real time. The text traces the specific lineage of the GPT family from OpenAI, serving as a perfect case study for watching Emergence catch the creators completely off guard. Let's trace that timeline, starting with GPT-2.
Okay, if we connect this to the bigger picture, when OpenAI scaled GPT-2 to roughly 1.5 billion parameters, a capability emerged that genuinely terrified the research team.
Love it.
The model developed the ability to generate incredibly coherent, multi-paragraph synthetic text that sounded chillingly human. It wasn't just predicting the next word, it was maintaining thematic consistency across long passages.
Right.
It was so surprisingly proficient at mimicking styles and generating plausible fake news that OpenAI initially refused to open source the full weights. That was the famous too dangerous to release controversy.
Yeah, I remember that.
They had not explicitly programmed a disinformation machine, they just built a larger transformer network, and the capability to flawlessly mimic human narrative emerged from the expanded vector space.
They hit a phase transition in pure text coherence. But then they scaled up again for GPT-3.
They scaled the compute and parameter count by 2 full orders of magnitude, pushing GPT-3 to 175 billion parameters. And at that scale, the industry witnessed the sudden emergence of the few-shot revolution we analyzed earlier.
Now,
The model stopped being a simple text generator and fundamentally shifted into a versatile reasoning engine.
that was the moment the entire landscape shifted. Developers stopped viewing language models as neat autocomplete parlor tricks and started viewing them as foundational operating systems. You could feed it a prompt with 3 examples of Python code, and it would dynamically learn to translate natural language into functioning scripts.
Exactly.
It was a massive nonlinear leap in utility, and that sets the stage for the architecture of GPT-4.
GPT-4 is where the scaling laws push the internal geometry into multimodal mastery. Through sheer scale and advanced, varied training datasets, the network developed the emergent ability to reason abstractly across entirely different types of data.
Not just text anymore.
No, it was no longer confined to text tokens. It could process a photograph of a hand-drawn website mock-up scribbled on a napkin, understand the spatial relationships of the UI elements, and immediately output the functional HTML and JavaScript required to build it.
Which is still crazy to see.
Right. Or it could analyze a complex multi-layered visual meme and output a logical explanation of why the juxtaposition of the images was humorous.
The leaps from GPT-2's coherent text generation to GPT-3's dynamic in-context reasoning to GPT-4's cross-modal logic mapping, none of those were explicitly hard-coded software features.
Not at all.
Each step represented a radical shift in capability that the engineers could not have fully anticipated
Yeah.
just by looking at the previous generation's test suite. They just built a dramatically larger engine, poured in exponentially more compute, and waited to see what kind of cognitive vehicle it would organize itself into.
Which brings us back to the core safety dilemma facing the industry today. The major labs are currently preparing to scale these foundational models up by yet another order of magnitude. If the mathematical pattern of emergent abilities holds true, the next generation won't just be a slightly faster, slightly more accurate GPT-4. The expanded vector space will almost certainly possess entirely new categories of capabilities that we haven't even conceptualized yet.
Unknown unknowns.
Exactly. Tools that are both incredibly powerful for developers and potentially highly dangerous if misaligned.
We have covered a massive amount of technical ground tonight. We started with the theoretical framework of phase transitions, the realization that intelligence in massive neural networks isn't a smooth, linear curve, but a series of explosive, geometry-driven leaps in capability.
Yep.
We dug into the hard empirical data from the Big Bench suite, proving that massive parameter scale alone unlocks complex tools like in-context few-shot learning and token allocating chain-of-thought reasoning.
And we also unpacked the nuance of the measurement debate, exploring how strict discontinuous rejects metrics might create the illusion of sudden jumps, while continuous token probabilities reveal a smoother underlying math. Yet even with continuous metrics, the structural leaps in logical reasoning remain undeniable.
And finally, we trace the history of the GPT lineage, watching those nonlinear phase transitions catch the industry by surprise time and time again, creating a massive, terrifying blind spot for AI safety and traditional CI/CD testing pipelines. Which leaves us with a profound shift in perspective to consider as builders and engineers.
The underlying nature of our work is fundamentally changing.
It really is. So I want to leave you with a final thought to mull over as you close out your terminal and shut down your IDE tonight. If scaling up the pure compute and dimensionality of a system guarantees the sudden, unpredictable emergence of capabilities that no human ever wrote, at what point does traditional software engineering become less about writing deterministic code and more about exploring an alien landscape we accidentally created?
That's a great question.
We are no longer just architects carefully building a house from a blueprint. We are suddenly botanists, trying to classify a dense, unpredictable jungle that sprouted overnight from seeds we didn't even know we planted. Keep building, keep questioning the metrics. We'll catch you on the next deep dive.
Take care, everyone. Keep exploring the space.